Hello, anatomy students. So over the past couple of lectures, we've been talking about neurons and how they function in the nervous system. And one of the most important characteristics that neurons exhibit is excitability and conductivity, which basically means that they are able to conduct an electrical signal through their cell membrane, which is then transformed by our central nervous system into some kind of a response, and in some cases, even memories. So I wanted to talk today about the action potential curve. The electrical activity of a neuron can be represented as a graph, a trace, which is what you see in the picture here. Here are your goals for this activity. After watching this video, you should be able to name and label all the phases of the action potential on the graph. You should be able to label threshold and explain its importance in the propagation of an action potential. Describe the changes in sodium and potassium channels in each phase of the action potential. Describe the movement of sodium and potassium ions in each phase of the action potential. Explain how and why the membrane potential changes throughout the progression of an action potential. And finally, explain the role of the sodium-potassium pump in the action potential. All right, so let's get started. Okay, so I just zoomed in on this action potential graph just so that I could have a little bit more space to kind of draw and so that you would be able to see clearly. The first thing that I want to do though is label the axes on my graph. So the x-axis is a progression of time. Oop, that's like too thick. So time is increasing here. And then on our y-axis, we have a measure of energy, which we'll label as millivolts. Okay, so the dotted line that we have here, this is where the membrane's resting potential is. That is typically labeled as a negative 70 millivolts. And remember that the negative 70 measurement of the membrane potential means that the inside of the cell is negatively charged, and that the difference in charge between the extracellular fluid and the intracellular fluid is 70 units. The reason, again, why our cytoplasm inside of our cell is negative is because it contains chloride ions, which are negative, and also because it contains anionic proteins, or proteins that will carry a negative charge. So that's why the inside of our cell is negative. So at our resting potential, so this is our resting. Remember that our neuron is ready to be stimulated. This is not a stable state, even though we call it resting. Remember that at this time, our neuron is like a salty banana. You have sodium on the outside of the cell, and you have more potassium on the inside of the cell. So we have sodium ions out. We have potassium ions in. The channels at the resting phase are closed. So channels are closed. Now you may have a few potassium leak channels, which are constantly open, and that's going to allow for the trickling out of a few potassium ions here and there. Remember that potassium ions are positive, and so that's going to contribute to the negative environment that is found inside of the cell, because as positive things leave the cell, the charge is going to become more negative. So that's what's happening during our resting phase. Now, the next line that we have on our graph is about a negative 59 millivolts. But like I said in the lecture, it could be negative 55, it could be negative 60. It's going to be in the negative 55 to negative 60 range. Negative 59 is known as threshold. Threshold is the amount of depolarization that must occur in order for an action potential to carry on down an axon. So how does the membrane potential become more positive to reach negative 59? Because remember your number line, right? Negative 70 is more negative than a negative 59. So when we're rising from negative 70 to negative 69, it must be because we have some positively charged particles that are entering the cell. And that's exactly what happens. We need to have enough sodium entering the cell. Sodium has a positive charge, sodium ions, I should say. We need to have enough sodium ions entering the cell in order to raise our membrane potential from negative 70 up to negative 59 in order for an action potential to occur. If that doesn't happen, then the action potential will not occur. And that's exactly what's happening here at the black arrow. So here, these are failed local postsynaptic potentials. So notice that they did not reach negative 59. So here's what's going on then. Between negative 70 and negative 59, what happens is that, and I'll just draw an arrow up here around my millivolts, what's happening is that we have some sodium channels are going to open, and sodium ions are going to start to trickle in. If enough sodium ions trickle into the cell to raise the membrane potential in that area from negative 70 to a negative 59, then we're going to have this chain reaction that occurs, right? So if the local area that receives the stimulus reaches negative 59, then that's going to cause sodium channels in the periphery to open and cause them to allow sodium ions in and cause those membrane potentials to raise up to a negative 59. And then that's going to cause other ones to do the same and others. And then it just kind of repeats, kind of like a wave. But remember that threshold has to be reached. If threshold is not reached, like in these failed local postsynaptic potentials, then you are not going to get propagation of an action potential. We've got to get up to that threshold, up to negative 59. Okay. So the next thing that I wanted to talk about is this. Once we reach negative 59, now we have our next phase of the action potential, which is depolarization. And that's what we have here. So at resting, our cell is polarized. We have positive charge on the outside of the cell, negative charge on the inside of the cell. With depolarization, we are closing the gap between the difference in charge from the inside and the outside. So we're depolarizing it. So just like that prefix D means like un or not. So we are not polarizing at this point. During depolarization, we have sodium channels open. And I should say that our potassium channels are open too, but they are opening very slowly. So we have sodium ions. Oops, that's a potassium ion. Sodium ions rush into the cell, while potassium ions stay in the cell. So now what you have is a great collection of positively charged particles inside of the cell. And that is what is driving our membrane potential to become more positive at about positive 30. So during depolarization, our membrane potential, which I'm abbreviating as MP, becomes positive because there's a collection of positive particles in the cell, right? So potassium stays in and you're adding more sodium coming in. And so now you've got this big crowd of positively charged ions that are found inside of the cell. And that is happening during depolarization. All right, when depolarization ends, and remember that the reason why depolarization is going to end, the reason why our action potential graphs are not different at different heights, is because the sodium channels are going to open for a very specific amount of time. And so there's only enough time for enough sodium ions to get into the cell in order to raise the membrane potential to a positive 30. So after the time for the sodium channels to be open is over, the sodium channels are going to close. Which means that our sodium ions are trapped in the cell. Now, remember our potassium channels? They were stimulated to open, but they open slowly. But by now, our sodium channels are open and our potassium channels are open, and our potassium ions are going to rush out of the cell. This is the phase that's called repolarization. During repolarization, the membrane potential, MP, becomes more negative. Why does it become more negative? Because positive particles, our potassium ions, are leaving the cell. And so that's going to cause our downward curve on our action potential graph. So this is called repolarization. Now, just like our potassium channels are very slow to open, our potassium channels are slow to close. So potassium is going to have more time to leak out of the cell. So it's going to leak out for a long time. And that's going to cause this dip in our membrane potential, which is a phase that's called hyperpolarization. So what's happening to our membrane potential is that it becomes more negative below resting. at this point, we're probably looking at about a negative 80 to a negative 90 millivolts. I'll put it on the graph here, negative 90. So it goes pretty negative. And the reason why is because our potassium ion channels are very slow to close. And so our potassium ions can continue to leak out. And again, since the cell is losing positive charge, because like the sodium ion channels are closed, sodium is trapped in there. It can't go anywhere. So sodium is still in there inside the cell, but we have potassium leaving. And that's going to drive the membrane potential to become very, very negative. Finally, at the bottom of this is where our potassium channels are closed. And now we have kind of a switching of our ions, right? At this point, our sodium is in the cell, and now our potassium is out of the cell. Now, our cell would be perfectly happy to stay there. But if it were to stay in this configuration with sodium in and potassium out, it would not be ready to accept another stimulus. And then that whole network would shut down. It wouldn't be able to propagate action potentials and communicate with other neurons and provide us with memories or responses or things like that. So this is a really dangerous situation. The cell has to get back up to resting potential. This is what's happening in this phase here, which is called our recovery phase. Our recovery phase. During our recovery phase, our sodium potassium pump is going to use ATP in order to push 3 sodiums out of the cell and pull 2 potassiums into the cell. So again, we have a little bit of an imbalance here, right? The sodium potassium pump is causing more positive particles to leave the cell than it is bringing in, because the pump works like simultaneously, right? Like you have 3 sodium ions that are bound to the protein at the same time that 2 potassium ions are, and then they switch places. So the pump is propagating this negatively charged cytoplasm inside of the cell because it's pushing more positive things out than it's bringing positive things in. But this is going to work until we come back to our resting membrane potential. And so here we are back at our salty banana, right? We have our channels closed. We have sodium out. We have potassium in. And our cell is now ready for another stimulus. So there's one more thing that I just wanted to mention about this graph, and that is our refractory period. Now, our refractory period is going to include hyperpolarization, and recovery. During the refractory period, we are not going to receive any more stimuli. like any stimulus that is received. Maybe I should say no stimuli is received. Maybe I should say that stimuli will not cause an action potential unless that stimulus is very strong during the recovery period. The other thing that the refractory period is going to do is to prevent bilateral travel of action potentials. Like, it's going to prevent action potentials from flowing from the axon terminal back to the cell body. Because remember, this action potential is happening in tiny sections of the cell membrane. So when one section of the cell membrane goes through an action potential, it's going to stimulate the next segment to go through an action potential, and so on and so on. So the pieces of the cell membrane that have gone through an action potential, they're in the refractory period. So even if a stimulus comes from the other direction, it's not going to cause an action potential, because the reason why is because our membrane potential is too negative to raise up to a negative 59 millivolts. So it's going to prevent backwards flow of an action potential. And so let's just explore that for just one more second. I know that I did just kind of explain it very quickly, but I just want to hit it home. So remember that in order for an action potential to occur, our membrane potential needs to reach a negative 59 millivolts. If the cell is at rest and it's at negative 70, you're just talking about, maybe, a 10 or 11 millivolt difference here, and that's it. So that's not very much. So that's a doable reach for a stimulus to cause depolarization. But when you're in our refractory period, you're talking about membrane potentials that are much more negative than our resting membrane potential. And so if we got a stimulus that came in here at the very bottom of our hyperpolarization phase, that would have to be quite a jolt in order to get all the way up to threshold, in order to create enough depolarization in the surrounding area to cause an action potential. But that typically does not occur. So that's why this refractory period is even there, is because of the very negative membrane potential that we have during hyperpolarization and then recovery. But as you can see, in recovery, our membrane potential is becoming more and more positive. It's still, coming up closer to negative 70. So, if we had a stimulus that was very strong that occurred here, that's not too much of a jump to get up to our threshold and possibly generate an action potential. Okay, so that is all that I've got for you on this action potential graph. You should, again, revisit numbers 1 through 6 and be able to explain each of them for each phase of the action potential. If you have any questions, let me know, and I'll talk to you soon. Bye-bye.